Start with the name of Almighty Allah, who is the best lover and who knows the real love. This is Ali Bakhtanu, along with my group mates Shahid Rashid and Abid Rasool. In today's presentation, we will define you our FIP project, which is Power Quality Analyzing through PMU or Phasor Measurement Unit. We did this project in the supervision of Dr. Hafiz Mudassir and our co-supervisor was Engineer Veerbhan. This is the agenda of today's presentation. In this presentation, definitely we will look at the introduction, problem statement, aims and objectives, methodology, results and discussion, and then at the end, conclusion. So let's start. This is actually a phasor measurement unit. You can see in the picture. Basically, what is PMU? You can call it a device. It is simply a technique or technology used in the power industry to monitor and control the operation of large-scale power systems. Like PMUs enable real-time monitoring and measurement of power system voltages, currents, and phase angles, providing a more accurate and comprehensive view of power system dynamics. Actually, why we are going to use PMU in our power system? Because we face some power quality issues in our power system. That's why we use PMUs in our power systems, especially in distribution sites. So which are the power quality issues in our power system? You can say PQ disturbances like voltage sag in our power system, short interruptions, long interruptions, harmonics, transients and surges, and also others such as voltage swells, etc. And this is a simple, you can say, a graph where you can see the problems or issues in percentage. Like 29% actually we have in power system voltage sag issue it occur most, and other as well, like short interruptions 18%, long interruptions 12.5%, and harmonics and transients and surges, right? So we have to overcome these issues and monitor these issues. These are the, you can say, wavelengths or signals of power PQ issues. You can see here harmonics, how it occurs, voltage sag, voltage swell. You can see voltage interruptions, under voltage, over voltage, sustainable voltage interruption, DC offset, and transients as well. You can see the signals, how it varies from input to output or in continuous. You can say power system, when there is a disruption, we can say face some issues like line to line issue. You can say three phase issues we occur in our power systems. So these are actually the signals of those issues. This is the problem statement of our project. PMU implementation in power distribution system has been rare at the level of consumers due to the cost and complexity of the technology. And a microcontroller based PMU is an alternative method for developing a more flexible tool of power quality analysis that may be definitely it will be an inexpensive and user friendly. And we also made a prototype of microcontroller based PMU, and we used Arduino Uno in our project. You will see in further presentation. Aims and objectives of our presentation. Our aim is to design and implement a microcontroller based processor measurement unit for monitoring and analyzing the quality of power in the power system. Our main objectives are to make a PMU or a prototype of PMU using a microcontroller technology capable of accurately measuring and analyzing power system parameters such as voltages. In our PMU, we will measure voltages, currents, frequency, and also active reactive power and phase angle. To make ensure that PMU can detect disturbances in the power quality such as voltage sags and swells, and our most of the work is on voltage sags. You will see further in our presentation. And then to compare the performance of the developed microcontroller based PMU against theoretical evaluation for power quality monitoring. Definitely we use some mathematical models and we embed that in our you can say microcontroller, then we analyze the results of our PMU with the mathematical calculations, you can say. This is some literature review in our project that PMUs have become essential in the restructured and competitive landscape of electrical power systems for precise real-time monitoring and control. and then another, you can say, article or research paper. They provide synchronized high resolution measurements crucial for maintaining systems stability and efficiency amidst growing renewable energy integration. Definitely nowadays you can see there are different resources, or you can say renewable energy sources. We have to integrate them in our, you can say, system for better power continuity, you can say. So PMUs offer digital high frequency up to 60 samples per cycle. You can say it is a little bit different from SCADA, because SCADA provide us 1 to 3 samples per cycle, but PMU provide us 60 samples per cycle monitoring. So while SCADA systems provide, you can see, lower resolution, just 2 to 4 samples per cycle, and also it has analog measurements. Initially used in the 1980s for high voltage grid stability, PMUs have evolved to support smart grid infrastructure and detailed power quality, you can say, PQ analysis, especially at the distribution level as well. In 2010, saw the rise of micro PMUs, you can say microcontroller PMUs, providing high resolution data for detecting PQ issues and localized setting as well. Recent developments focus on micro PMUs in residential and small scale environments for advancing PQ monitoring and renewable energy integration. Advances in micro PMUs are significant for distribution level PQ monitoring and integration into smart grids, adding dynamic and adaptive grid measurements, you can say. And then definitely there are cybersecurity and data measurement and are critical concerns as PMUs become integral to grid operations, particularly due to wide area interconnections. Definitely when there is an internet connect with our power systems, then definitely there will be cybersecurity issues. So challenges like cost, complexity, and cybersecurity need addressing. Microcontroller based PMUs offer a portable, cost effective solution for distribution side power quality monitoring, enhancing the integration of renewable energy sources. So this is our methodology for the project. First of all, definitely project initiation and planning. This phase involves defining project goals, objectives, scope, and resources. Then literature review. Researchers review existing literature and develop a conceptual design based on prior knowledge. System design and simulation. Use simulation tools, LabVIEW, MATLAB Simulink, you can say, to model the power system and simulate various power quality scenarios. Then PMU implementation, interface design in PMU, then power quality parameter monitoring, implement software tools to visualize and analyze voltage magnitude, frequency, and phase angles. Also, you can say active and reactive power in our PMU. Development of recommendation based on findings, develop recommendations and guidelines for the, you can say, deployment of PMUs in power systems. Then project reporting and presentation, findings and results are compiled into a report. These are basic two components we used in our hardware, you can say, in our project. One is, you can say, CT simple, it's a current transformer, and other is VT, you can say, voltage transformer. You can say their number is ZMPT 101B voltage sensor, and the number of, you can say, current sensor is SCT 013 CT. And then we simulate our PMU and MATLAB. You can say here a circuit, you can say power factor through model, through mathematics we proved, and then you can say apparent power as well. So simulation measurements of active power, reactive power, power factor, and apparent power through simulation we did in MATLAB. And then this is the result of our simulation, the model we made in MATLAB, and then we saw their results. You can say wave graph where amplitude and time, amplitude time graph, you can call it a wave graph for the simulation of our project. Then we move forward to our hardware where we use CT, VT as I mentioned in previous slides. And here you can see this is where from where we get input to our PMU. This is a CT and this is VT, and this is a voltage regulator. You can say we increase and decrease the voltage level, and then we analyze the results, how it impact on our, you can say, loads. These are the results, you can say, voltages. In starting, when we apply voltages, it's 224, which is normal in our, you can say, houses or our gates when there is a single phase. Then when we start decreasing voltage, then it decreases from 224 to 223, 222, 221, and later on we decrease it till 100 volts, and then power off. These are the results of current measurement. Here are current 0.47 ampere, 0.42, 0.46, and it's continuous varying, you can say. This is the phase angle, power factor, and frequency. Phase angle is 4.9, 4.9, 4.9, and when we start decreasing, it becomes 30.9 and 40.939. It increased basically as we decrease the, you can say, regulation. And frequency, almost it's same around our, you can say, decreasing and increasing. It's 50.07 hertz. This is our power factor, 111. Actually, this is power factor is 1 because we are using only resistor load, but if we start using other loads like inductive, then definitely power factor will get affected. But here we can see there is some little bit decrease in power factor because uh, contribution of, you can say, wires is also there, so they may appear there's a reactive power, so it's small decreasing. Then active and reactive power, you can see from 6 watt, 3 watt, 7 watt, it's continuously changing, and 93 watt, 96, 96, 94 watts. It's active and reactive power in our results of our PMU. You can say a prototype PMU. Then these are the final results. We can say voltages 224 to 226 volts, currents from 0.42 to 0.47 ampere. Our frequency is also within the limit, which is 49.5, 49.7 to 50.2. It is permissible limit in our power systems. Then phase angle 4 to 5 degree, and then power factor from 0.93 to 1, because we know we used a resistor load, so that's why it's 0.993 to 1, and active power from 94 to 96 watt, and reactive power 3 to 10 watt. And then we can conclude here. You can say it's a conclusion: designed a cost-effective microcontroller based PMU using Arduino Uno for real-time power quality analysis, and then achieve high resolution, you can say, measurements of voltage, current, frequency, phase angle, power factor, and active reactive power. Demonstrated crucial role of micro PMUs in enhancing power distribution monitoring, validation of the PMU's performance in practical scenario. You can say proving its effectiveness for geared application. This is some future work which we can continue, or it can be continued throughout, you can say, project. The comparison of our microcontroller, our own prototype, with the compact Rio or Stereo and Fluke. Both are the already, you can say, built-in meters which can also calculate like power, frequency, and power factor, active reactive power, voltages, currents. So we can compare our own microcontroller based PMU with the compact Rio and Fluke, and it can be implemented on different loads. Like we use just resistor load, but we can replace it. We can add another reactor load, or you can say inductor load, like it can be a motor or something else. Then different testing on different environmental conditions, we can implement our PMU on geared stations, and we can monitor on in different conditions how it behave or how it acts. And then basically it's reconfigurable by adding more parameters such as THD. It's reconfigurable, we can add more parameters in our, you can say, prototype as well, and can be implemented to more advanced microcontroller like ESP32 Wi-Fi module. These are some references, you can say, 10 references, 10 research papers throughout. We gone throughout them, and then definitely we got some data from these research papers as well, which we use in our prototype of PMU. Thank you.